Hello, everyone. Today on this call, I got Keryk with me, and we're going to be talking about Z-board, the FPGA and ARM processor in one chip.
Hi, Martin.
Hello, Kevin. Great to have you here. How are you doing?
Good. I'm doing good. How are you doing?
Awesome. I've been waiting for you, and then you didn't come, and then we realized that you got the wrong link.
Yeah, the link that I said it said it was for only October 30th, which was the meeting on Friday that we rescheduled until Monday. So I guess I had the wrong link.
Yeah.
But thanks for sending me the right link. It's good to talk to you.
Great to have you here. So the reason that I wanted to reach out to you is because I found the Z-board extremely interesting. So it's an ARM processor and an FPGA in one chip. And I want to know more about that. And I want to find out about the tooling that is used to program it and about the workflow that is used to develop software for it. And also, if you have the experience, it will be interesting to know how to get started. What is the fastest way to get started on Linux?
Yeah. So we've been working with Zynq 7000 since about 2011 when we came out with the Z board, and we've come out with a number of different boards since then. When we came out with Z board, we originally intended that to be a development only board, and we found that a lot of folks were using that in their end production systems because it was easier to just use a Z board rather than take the design files and redesign that for their own chip down solution. And so we came out with another product called Mini Z, and so that Mini Z also had a Zynq 7000 on it. It had basically the same features of the Z board, but it included 2 expansion connectors that would allow somebody to connect that up to their own carrier board, so they could target that to their own application-specific type platform. So if you look at our website,
I will actually share my screen so we can look at it.
If you go to if you go to element 14, that's probably like the best place to find. Oh yeah, zboard.org. So the zboard.org is our website that's currently migrating over to element 14, which is the world's largest online engineering community. But we have a lot of information available on zboard.org still. You can see, there we have the Mini Z board. That was an evolution of the Z board that's targeted to the Zynq 7007S device. But we have all those same boards that you find on zboard.org. They're all supported on our element 14 site. So probably the easiest way would be to just go to the search bar. Oh, okay, yeah. So you're already here. This is the Z board community. So it has links to each of our different boards. So after we came out with Mini Z, we came out with another board. It was called Pico Z. So it's a little same sort of devices on it, but it's a smaller, more ruggedized form factor that's targeted for a slimmer profile. And all the boards that we've developed since then, they all undergo temperature testing and some environmental testing to make sure that they cover industrial temperature ranges. We have industrial temperature versions of each of the boards. So then we came out.
This Ultra96, is that something? Is that like a carrier board for Ultra Z or something similar?
Yeah. So this is this Ultra96. You can see I have one here. So it's a I gotta put it in front of me or else it disappears. So we have this board. This Ultra96 is what we would call a single board computer. And so it's similar to Raspberry Pi, but it actually follows a standard. So if I take the camera board off the top of it, I have this little camera board that plugs right into the top of it. So this would be it follows the 96 boards standards for single board computers. This is actually the consumer edition form factor. And it has an expansion port up here. This is like a low speed expansion port up here. And then it has a high density, high speed expansion port down here. So you can run like GPIOs over this one, and then you can run LVDS signaling over the high-speed expansion port.
Mm-hmm.
And here we have like this is a camera module that we came out with recently. It has two MIPI image sensors on it and an ISP, and that sends a MIPI CSI stream down to the target board where the Zynq UltraScale Plus can pick that up and bring that in as a V4L2 interface under Linux. So you basically you can use stereo imaging and bring that in on your platform for doing things like machine vision and AI on a platform.
Right. And that is running, the Linux is running actually on the same chip then.
Yeah, so Linux is running on the Zynq UltraScale Plus. So it's running an embedded version of Linux. We have a few different flavors that are available. The Xilinx supported tools are a set of tools called PetaLinux. And so that's basically a set of tools that are built up around Yocto. And so you can build your own targeted embedded Linux image for this board that's specifically targeted for your application. And if you want to add additional stuff, it's just a matter of adding in additional Yocto build recipes. There's also a version of Ubuntu that has a special set of tools that are targeted for the Xilinx Zynq 7000 and the Zynq UltraScale Plus devices, and that's an image called Pink. It's PYNQ. And so that Pink image, it's built on top of Ubuntu, but it included some extra libraries, and it includes Jupyter notebooks. And under Pink, this would allow Python developers to access any sort of hardware peripherals that they develop inside of the programmable logic. So the best thing about the programmable logic is basically like the blank take of silicon. You can create it to do whatever sort of function you want. You could create it to make a custom accelerator. You could turn it into some glue logic to access some special device that you may not be able to find a standard peripheral set for with another ASSP. And so that's the really creative thing about the programmable logic is you can basically get it to do whatever you want. And the thing that's really nice about Pink is that it gives Python developers the ability to access that same sort of hardware, whereas in the past, you would have had to have been a C or C++ developer to create a driver to access that custom piece of programmable logic across the ACAP interconnects. So the thing that's great about Zynq 7000 is you have these high-speed ACAP interconnects between the ARM processor and the programmable logic that allows you to transfer data very rapidly.
Yeah, so you can basically have a parallel interface inside the chip directly, right?
Yeah, exactly.
That's really cool. And when it comes to programming or making this binary that goes into the FPGA, what tools are available to Linux developers that basically build that image?
Yep. So if you're a Linux developer, you can do everything inside of Linux. There's a set of tools that Xilinx has. It's called Vitus, and so you can install Vitus. It has all of the hardware synthesis tools underneath it. It's a Vitus. So if you look up that on the Xilinx website, you can find more information about that one. Oh, sorry, VIT. I'm sorry, it's VITIS. Vitus. And let me paste this one in the chat. So this is a tool that called Vitus AI that builds on top of the Vitus tool that my colleague, he put something together here recently to show how to run it on a number of different platforms that we have.
Okay. So this is essentially running on one of these boards in combination with the camera interface, FPGA, and Linux on the board, right?
Yeah, so that link that I just pasted in there, that one is an image that was built with the Vitus AI tools under Linux running on an x86 machine. So you still have a build machine where you're building your targeted embedded image. That embedded image then gets loaded onto the Ultra96 device or the Mini Z device or whatever device it is that you're targeting. then you can run that platform. But the suite of tools is it's called the Vitus Unified Software Platform. So what Vitus allows you to do is allows you to create a hardware. You start with a base hardware platform, and you can add in additional hardware acceleration capability using the tool directly from a basically like a software design cockpit. You're creating hardware using the underlying tool. So you can take like a C program and you can analyze a portion of it. Maybe there's a bottleneck that you're undergoing where you're doing these tightly nested for loops or something like that. You can basically unroll all those loops and perform those calculations inside of the programmable logic using this Vitis AI tool. It will actually create all the data transfer wrappers, and it'll create the HDL code and synthesize the HDL code for the programmable logic portion of it. So that way you don't have to worry about being a VHDL developer in order to create custom hardware. You can actually create it from your C application.
So this is basically compiling AI algorithms into programmable logic so they run faster.
Yep, you can do that. They actually have, Xilinx has a dedicated AI processor called a DPU. It's a deep processing unit. And so it's a piece of IP that you would load inside the programmable logic that acts as an AI algorithm accelerator. So it's really good at doing vector math and accelerated math computations around AI algorithms. And then you can take a portion of your algorithm and you can offload it onto that processor. And that first link that I sent you there and on Hackster.io, that's from my colleague Mario Bergeron. He put together a tutorial on how to build up an entire AI platform from scratch using the Vitis
so the beautiful
AI
thing
tool.
here, then, the beautiful thing here is that you can this DPU that you mentioned. It's not another chip. It's actually something that you load into this Xilinx logic chip, right? It becomes a
exactly.
soft core.
Yep, it's a soft-core processor that's running inside of the programmable logic, and it's optimized for the math operations that you would find on inside of AI algorithms. So like heavy vector math, like matrix multiplication and things like that, are very, very easily handled by this processor. And so that's really useful for a lot of different applications, like particularly automotive applications where you're trying to reduce the total amount of latency in your system. And you don't want to spend time like offloading that to a separate AI processor. You can basically do it all inside of the same chip. So you're saving yourself not only a lot of space on the board because you have two processors that are tied very closely together, but it also saves you power because now you're not having to power two separate chips. You're basically powering the same chip, just moving data between a processor and the programmable logic. And then it also gets you the lowest amount of latency because you can optimize your algorithms to run on that DPU processor, that deep processing unit inside the programmable logic to help accelerate whatever AI algorithms you may be running on your embedded platform. So in terms of automotive, latency is everything, right? Like, especially if you're trying to do a vision-based system where you decide whether you want to go, push the accelerator or push the brake. If the system's making that decision, milliseconds can make all the difference in terms of braking because, you may have like a pedestrian or something, and if you wait an extra 10 milliseconds, that's an extra 10 milliseconds that you haven't stopped the vehicle before you hit the pedestrian.
Right. So if somebody, let's say, to simplify the process for somebody just starting out, what is the fastest way from Verilog to actually being able to access that logic from Linux running on the chip?
Yeah, so if you want to get started with the traditional FPGA design path, that would be to go down and learn like a Verilog language or a VHDL language. All the Xilinx tools still support that flow, but they have these more accelerated flows where you can enter into the development process, without having to go and learn those languages. So like the Vitis AI tool, that would allow C or C++ developers or even system Verilog developers to start creating their application from inside of that tool without having to learn any VHDL or Verilog. You just basically start writing code. You can profile your code, find out where all your bottlenecks are inside the code, and then you can create these custom accelerators by, you basically wrap your code with these set of pragmas, and it tells the tools like, hey, I want to synthesize this portion of my C code into a hardware accelerator, and it'll run it through the synthesis tools. They basically have like a C Gates type tool that's running behind the scenes, and you can turn that into a custom hardware accelerator, and it helps do all that stuff for you.
So
then
Vitis essentially is translating C code into FPGA code, into logic.
Yep, definitely. Vitus is capable of doing that. So you don't have to be a VHDL expert in order to do stuff inside of the programmable logic on a Zynq 7000 chip. The Vitus program will handle that for you.
So how does that translate? How does the software translates into the logic? Like, let me just clarify the question. So let's say I have a sequential program in C, and it gets translated into logic. Is it still going to run is it still going to be synthesized as a sequential set of operations?
So yeah, absolutely. It will still be synthesized as a sequential set of operations. So where you're going to get the most amount of performance boost is where you're optimizing parallelized functions, to where you can run multiple math operations in parallel. So I mean, one of the things that programmable logic is really good at is matrix multiplication. So if you're doing a bunch of matrix multiplies, it can help out with that. If you're doing a bunch of parallel math operations, there's these little pieces of hardware inside the programmable logic called DSP48 blocks. And so that can help you with different multiply and accumulate functions in breaking those out into parallel. But you're right. If you're trying to do something inside of a sequential algorithm, you may not get that much of a performance boost because the FPGA still has to do that same sort of sequential logic in order to get the same result. But where it really helps is where you can parallelize things, because you can, rather than having, a 16-core processor where you're running your algorithm in parallel across 16 cores, you can create just a very specific set of hardware that's performing that one math operation, or those few sets of math operations that you're running inside your algorithm, and it executes only those ones. So you're not dedicating like a huge amount of resources like you would with a 16-core processor to perform that math calculation. You're creating only the exact set of hardware that's needed in order to optimize the calculations that you're doing for that math operation. And then that little piece becomes your hardware accelerator.
Okay, so the compiler, it'll be the Xilinx tool that the optimizer will actually look at the code and decide that this is a for loop that is kind of doing sequential work, and we can optimize this by translating it into an FPGA core. Is that how it works?
Yep. Yeah, exactly. Those tools will extract out that piece of logic that you've wrapped with the set of pragmas, and it'll wrap it with the data movers that are needed to move that into the programmable logic. It'll also create the hardware acceleration core, and then once that result is ready, then it'll also bring it also help you make the data mover to move that result back into the processing subsystem. So your ARM cores where you're running the rest of your software.
Right. So then it's necessary. You compile this code basically with Xilinx compiler, and it results in a binary that is automatically optimized. So when it runs, it will automatically use the programmable logic to accelerate those operations.
Yep. Yeah. So I mean, if for developers that are new to programmable logic, that's definitely the recommended way to go. If they're, if you're talking to hardware engineers who are kind of looking for more of the traditional flow for doing FPGA development, there's a really nice book that somebody developed. It was, I believe, somebody from the University of Strathclyde put together this book. It's called the Zynq book. Basically, it walks you through all of the basics of how to get started with doing the programmable logic development and everything. So that's a great resource. We have tons of free resources that are available on that Element 14 community site that that you were looking at earlier.
Mhm.
And we have support forums where the folks from my group, we monitor those support forums directly, and we answer people's questions on the community. That way other people can benefit from the answers that go out to people asking questions. It's kept in that forum, support forum format. So let me post some links for that. So you originally asked about like Zynq 7000, and let me mention really quick, like for this Ultra96 board, one thing that is special about this Ultra96 board, it has the newer generation of Zynq. So this is a Zynq UltraScale Plus MPSoC. So this is a so whereas the Zynq 7000 was a single core processor, this one is a dual. Whereas the Zynq 7000 was a dual core processor, this one's a quad A53 processor. So quite a bit more resources that are available on this one. And then Xilinx is also working on another device. You may have heard of that one. That one is the Versal device. And so that one will have an even more sophisticated architecture to it.
Which one?
It's a Versal, V-E-R-S-A-L. It's the link to it.
Okay, so so this is kind of designed to eventually maybe even replace compute platforms that use the GPU, right?
Oh yeah, definitely, yeah.
So you would be able to accelerate essentially anything and parallelize anything through programmable logic.
Yeah, you definitely see like a lot of GPU technology being deployed nowadays because you're able to get a lot of parallelization out of those platforms without having to do a whole lot of work of converting your algorithm over to another type of processor. But this platform, the Versal platform, that one is definitely targeted towards being able to do those parallel computations inside of the programmable logic. If you have specialized math operations, you can do it inside of these math engines, or they call them AI engines, that are spread throughout the chip. And then of course you have, I believe, Cortex A72s on this device for doing the processing. But this one's Xilinx's latest chip in that sort of family where you have processors and programmable logic all on the same chip.
So this is going beyond Z-board. It's sort of the latest hardware.
Yeah, so this definitely goes beyond Z-board. So a lot of these platforms are still like early access platforms, so you still have to have, apply for being able to get a hold of a development board that has a Versal device on it. But that's something that we're looking at Avnet, coming out with a development platform at some point in the future on that, once that becomes publicly available to everybody.
So what are the requirements to become a developer and sort of get access to the SDK for this platform?
I think it all depends. A lot of it depends on what your plans are for it. Like, they don't want a lot of folks, kind of coming in and just kicking the tires on it. Like, if you have a real application that you're targeting, like an automotive or industrial or even aerospace and defense type applications, like, they want to make sure that the people who are developing a product right now, that they're getting the resources that they need in order to do that. Once we have a generic general purpose development board available after the device is fully released, then everybody will be supported on that, including folks like you and me, like, who are doing like development work around that. What's your main application that you're focused on?
I'm focused on microcontrollers and motor control. So
okay,
I work on embedded systems.
Okay. Do you do only like education stuff, or is it
no, I'm a consultant. I'm a consultant.
Yeah.
I do firmware development, and
okay.
I also do education because it's really a way for me to also clarify my knowledge and try to kind of achieve, because when I achieve the result of somebody else getting results with what I teach, then I know that what I teach is good stuff and it makes sense.
Yeah, no, that makes a lot of
I
sense.
found this way that really helps me to sort of to clarify my own knowledge. And the more I do the workshops, the more I do education, the more I kind of feel like, wow, this is such a good way for me to learn as well. And it's because, you know, we are doing a lot of things on a day-to-day basis, and we kind of take it for granted. And then when we try to explain it to somebody else, they go like, oh my God, like, I don't understand anything. And that kind of means also that maybe we don't understand exactly what we're doing. So maybe we're just doing it and it works, but we don't really think about it. We don't give it a second thought. So I think that's really a powerful way. And that's, so I want to understand not just embedded systems, but also hardware design and anything that's related to product development on embedded systems. And that's what I want to also give to the students, an ability to build products quickly. So I want them to be able to start and quickly be able to put together an idea, to realize the idea. So I'm very interested in, one of the things I think with those higher end FPGAs is that it can be very overwhelming for somebody who is entering this field to start developing real hardware on FPGAs, because there's so many tools, and there are tools from Xilinx that are complete IDEs that do a lot of work for you. And then there is, so people, when they get started, they kind of get overwhelmed and they give up because maybe they don't really never get up to speed with that. So what I'm curious about is sort of breaking down this process. For example, if we look at some of the lower end FPGAs, there are Linux tools that allow you to build the image for the FPGA. Is there something similar for Xilinx where you can actually just use the actual commands for compiling the hardware, the hardware description language into FPGA binary image?
Yeah, no, that's a really good question. Yeah, so there is a GUI for the tools, which you can use to sort of explore like how to connect up all the blocks. But actually, once you've connected up all those blocks, you can export your design as an entirely scripted build file in a TCL format. So TCL is a scripting language that is commonly used in like the ASIC industry, and so Xilinx designed their tools around being able to drive that tool using this TCL language. So you can basically script your whole entire design. In fact, let me send you a link to this latest link that I'll send you. It's a link to our HDL repository on GitHub. So if you click on that link, I put that inside the group chat there. Let me know if you're getting those links. And
yeah, I'm getting those links. Can you see my screen?
Yeah, I still see the Vitus screen.
Oh, that's interesting, because I've been changing the screen, so I've been clicking all the links.
Oh, okay.
Right.
It just doesn't appear to be updating on my end.
Let's see. You still see the Vitus screen?
I still see Vitus Google search. Okay, now I see just your video.
Yeah.
So your desktop went away.
I'm gonna share it again so that we get the screen. Can you see it now?
Oh, yep. So now I can see it now. So
do you see it scroll?
Yep, I see it scrolling down. So you're looking at our GitHub. So okay, so this is an example of what I was talking about, where we scripted up all of the HDL designs that we've done. This looks like the README needs to be updated. It still says 2017.4, but we build all of the underlying hardware platforms using this tool, and you can actually call you call the Xilinx tools from these build scripts, and everything can be built entirely from the command prompt. So you don't need to you don't need to do everything inside of the GUI to rebuild a particular design.
So can I build it in Docker, for example?
Yeah. So like if you had let's say you had like a Linux platform, if that's what you're familiar with using.
Yeah,
like you,
yeah, but mostly like, for example, automatic builds. If you're just building something on a VPS, which just generates you an automatic build, then you need to have command line tools to build it. So you just basically want to kick off a build, and then it builds that, and maybe it does also builds verification suits that tests the hardware, and then you get a final image. Maybe it's also some firmware involved in it, but just sort of building everything from command line using just compilers and command line tools. I think that's really useful for people, so that so they can use they can write VHDL or Verilog and then easily get that into the chip. So I'm curious about that workflow, and really how can somebody do that if they're familiar with Linux, they're familiar with how to build software, they're familiar with hardware design, and now they just want to sort of get up to speed using this Z board or using the new chip. Is it using this Avnet HDL repository that they can get up to speed with that?
I would say, like, if you're just learning the tools, I think it's probably best to go the GUI way, so you understand how the tools putting your design together. Or if you're a C developer, using the Vitis tools to see how the tool is creating your hardware accelerator from your C language. I think once you kind of understand that paradigm, and then you want to be able to just reproduce your results over and over and over again, then going with the scripted flow is definitely the way to go. Because that's kind of how we started out here. Is like we do everything inside of the GUI, get the platform running, and then we say, okay, well, now that we have everything running, let's script that so that way everybody can reproduce our results the same way without, maybe without using the GUI and maybe accidentally clicking the wrong button or doing some out of order sequence inside of the GUI. It's much more easy to create reproducible results. I pasted a few links though. There's a Xilinx getting started link that my colleague Dan Roswood. So it's the one that says, it's maybe 4 links up.
Can you see my screen right now? Is it updated?
Yep.
Yeah. Cool.
Yeah, so this is a tutorial that my colleague Dan Roswood, he put this together, and so it was recorded. So this one's about an hour long. So this kind of gives an overview of, how to get started, what is it that you need to focus on, from a Xilinx technology perspective, and what can you expect in terms of results from those tools. And it targets that Ultra96 board that I was showing you. So this is our main development platform that we're using right now. It's the lowest cost Zynq UltraScale platform that's available today. So
okay.
It's a pretty good platform to get started on. The next link underneath there is a link that my other colleague, Mario Bergeron. So this one's the Ultra96 Getting Started link. So that's another, I think it's the one right above that. So the Ultra96 Getting Started. So this is an event that we just put this one on recently in August. So this one, it requires a registration, but my colleague Mario Bergeron, he walks through everything that's needed on this same board in order to get the AI acceleration up and running on this platform. And so he even shows how to go through and do some OpenCV acceleration on this platform. So that's a useful one. And we just released that one because Xilinx has a design computing contest, and it's called a adaptive computing contest, and that was that other link on the tab just to the left of this one. It says adaptive computing.
That one.
In your browser. Yeah, so this is a contest that Xilinx has going on where participants can design their own adaptive computing algorithm, and Ultra96 is one of the hardware targets for this, but they could, participants could win up to $10,000 worth of prizes in this. So this is a design contest that's ongoing by Xilinx, and Hackster is one of our community forums that we have available here at Avnet. And so, if you have students that are looking to win some prizes, to give them some cash to work on some of their other projects, this would be something really useful to help motivate them to getting into learning how to do some of these more advanced things on the Xilinx platforms. But that event registration one, just to the right of that, that was a tutorial that we put together specifically for Ultra96 to show contest participants how to get started really quickly, so that way they can have a base platform to start with for doing their own AI acceleration for the contest.
Is this a live event or is it recorded?
So this one is recorded. So it was live when we broadcasted it back in August, but it was then recorded.
Okay.
We came out with it in August when we launched the that adaptive computing contest with Xilinx.
So
those are.
Yeah, go on.
I was just gonna say those are some good resources for people to use if they're looking to get started really quickly and get something up and running fast. Would be to follow these few webinars here, and then sign up for the contest, and then that'll help set them down a path to where they can start developing rather quickly.
That's awesome. And one more question. So, like on most of the other boards that are running ARM, it is very easy to build a full system using a system like Buildroot, for example.
Yeah.
How difficult or how would one go about integrating Xilinx tools with, for example, Buildroot? Let's say you build a system using Buildroot. You have your little firmware with all your packages and all your custom software. And now you want to accelerate some parts of it using Xilinx FPGA. How would you go about? Where do you get started? How do you sort of get up to speed with that without getting overwhelmed?
So I haven't seen a whole lot of good tutorials around using Buildroot. The primary tools that are used to build Linux for the Xilinx platforms are the Yocto tools. So they use Yocto build tools in order to build that. And then the sort of tool that they wrap around that helps manage the software world and the hardware world is a tool called PetaLinux. And so PetaLinux has integrated into it. Let me paste a link to our other GitHub repository for PetaLinux. But basically, the PetaLinux tools allows you to build a Linux system, and then it also allows you to pull in your hardware configuration and use a tool inside of the Linux development tools called the device tree generator. And the device tree generator allows you to create a device tree from the platform description of your platform. So like, you would have like a platform description for any custom hardware that you build on Ultra96 that are connected up to the ARM processor. You run it through the device tree generator, and that generates this device tree source file or a DTS file. And then you would just compile that with a DTS compiler to create a device tree binary or device tree blob file. And that's what tells the Linux kernel which custom pieces of hardware are available on your platform for it to access. And then it knows how to tie those drivers into accessing each of those pieces of hardware. So there's a tool called PetaLinux. What we've also done is we've also sort of taken the approach that I was describing before, where we don't want somebody to type in a whole bunch of different commands and maybe type a command incorrectly or maybe do things out of sequence. So we've actually scripted everything that we built for our system. So if you go inside of here and you click on the scripts folder, you can see a build script for the PetaLinux platform for every single one of the boards that we create here at Avnet. So you got your Ultra96 board, there's the Ultra Z boards down there, and then Xilinx, of course, they already release a PetaLinux BSP for Z board, so we don't include that one here because Xilinx is already building that one.
So that BSP, is that sort of is there a Git repository for that Linux kernel that contains all the necessary drivers for?
Yeah. Yeah. So behind the PetaLinux install tools, Xilinx maintains their own branch of the Linux kernel. So they update their branch with every major Linux kernel LTS release.
And where is that?
So that is, I'll send you the link to it.
So that device tree that is being generated is generated after the tools have converted. If they start from C code, they convert that to HDL and then into hardware, and the device tree is generated from that, right?
Yeah. So if you think about like the way that flow would work, you would start with a base hardware platform. Then you would use those Vitis tools to create your C algorithm. You can use that C algorithm to profile that C algorithm, figure out where your bottlenecks are, create your custom hardware accelerators with that. Then you would export that whole entire hardware platform out to PetaLinux. PetaLinux then picks up that hardware platform. It analyzes the hardware description. Basically, there's a file inside of there that provides a description of what the hardware looks like, and then it runs that through the device tree generator in order to create the device tree that enables Linux to be able to access the custom peripherals on your platform. And then it can also build it's just like Buildroot, where it builds like a single image, like it builds like a bootloader where you can use to boot the system, and then it builds up an image.ub file, which basically contains like your kernel and your device tree, and it can also contain your root file system as well. So you basically get those two outputs from the PetaLinux tools, and then you can boot up your platform from just those files.
That's really good, right? So, so once you have developed your hardware and you have the device tree and you build the Linux, then you can actually start developing device drivers for whatever hardware that you have designed.
Yep.
So that's kind of the workflow that follows, right? But let's say somebody has already a core they want to like written in VHDL or Verilog, and they just want to build that and be able to access that from Linux, and then write a device driver. Maybe they even write the device tree nodes themselves for that core. How do they get started in the quickest way possible?
I guess it all depends on whether or not they want that driver to be pulled into like the main line. So like that's like the tricky part. Like if you're doing just your own device driver and you're not worried about pushing it into the Linux kernel mainline, it's really very easy to access that custom hardware accelerator, because you basically have access to a hardware accelerator that's inside of the memory map of the ARM processor. And so then you would just need to know, what addresses that's located at, which is usually something that you're provided directly by the device tree generator. So you could pull that information out of your hardware platform. Actually, I think at one point we created an example of how to do this, and we provided that. I don't know if it's been updated recently, but you basically just perform memory reads and writes to your custom peripheral, and you treat it just like it's any other piece of peripheral hardware on the system. So if you have something that looks similar to another device, let's say it's like an I2C driver, you can use the I2C subsystem under Linux to create a driver for that device. Or let's say like, your device has, like we're going through this right now with like the camera devices that we have on that Ultra96 board. So like we're creating like a set of V4L2 drivers that go behind this ISP here that format an input device for a specific input resolution. So it just becomes just like any other piece of hardware that you're accessing on the platform. You're accessing just a set of register interfaces that are on the processor memory map.
Okay, and those addresses, so where the peripheral ends up in this memory map, is that controlled in the tool somewhere that compiles the hardware, or is it, how does one determine where it goes, or gets those addresses?
Yeah, so it will place it in a default location. You can go in and you can fine tune that to a different location inside of the tools. When you create like a hardware platform, the GUI creates a way for you to set up that specific address, but you can change that address. And like if you go through our HDL scripts, you can see like inside of there's like specific ways that you can assign those addresses to specific ranges. So if you're looking to have a certain amount of memory space in between different hardware peripherals. Another thing you might want to consider too is like you can separate access for those hardware peripherals and make that different for the different processors that are on the system. So you could have like say an RTOS that's running on say one of the R5 processors on the Zynq UltraScale Plus device, and you can kind of sandbox that memory space so that only the R5 processor can access that memory space to get access to that peripheral. Then you can have Linux running on one of the Cortex A53s, and so then that provides you a little bit of system partitioning, so that if you have a piece of software that's running under Linux that something goes wrong, it can't accidentally access that system critical piece of hardware that the R5 processor is having access to.
Okay, so it's possible to separate out memory areas because they're both sharing the same memory, right? The FPGA and the ARM processor.
Yep, they share the same memory, but you can actually go in and you can configure it, much like you would see.
It's done in hardware, right? It's not done in device tree; it's in hardware.
Yeah, it's done in the hardware, so you can partition out that memory access using the hardware.
Right. This sounds really cool. The only part where it's still not 100% clear for me is sort of the workflow through the tools, and maybe just sort of compiling a simple Verilog program and getting it just through command line tools into the FPGA. That, I think a tutorial on that would be really cool.
Yeah.
For somebody who just just maybe a simple UART driver that communicates with the GPIOs, and so that it can be built by just downloading a GitHub repository and running a script.
Yeah, for somebody that's looking to get started, really quickly, doing something really, really simple, we do have like a set of tutorials that are available for free that are a little bit more in depth. So like if you have students that are willing to dedicate, some amount of time to learning that, we have these mini Z workshops. So I'll paste a link to that. So this is like a free 3-course bundle. And if you think about each of those courses takes about like 6.5 to 8 hours, so about a day each. This walks you through doing the software development, so it gets you familiar with the software tools. It walks you through doing the hardware development. And then it also shows how to use PetaLinux to integrate a sensor onto MiniZ for tying that into an IoT application. So it shows you how to, the culminating event in this exercise is capturing information off of a little sensor, packaging it up inside of an MQTT message under PetaLinux, and then sending that up to the cloud so that you can see it posted up in the cloud. So that's something that we came out with recently. If you want something that's a little bit more sophisticated than that, we have the sort of same basic portion of it, that training, and then we also have 3 advanced courses that get built on top of that as well. Those ones are available at the second link that I sent you there. Those ones are part of a bundle. You can get all 6 courses available for $59. So if you're,
can you see my screen?
Yep.
Awesome.
Yeah, so that one's a little bit more advanced because that one's targeted to the Zynq UltraScale architecture. So we charge for that one. But the mini Z one, that was something that Xilinx was really excited about getting that out to folks. So they actually subsidized the mini Z one and made that available to everybody for free.
Mm-hmm. Yeah, that's a good way to get started. And then they get once they get comfortable with that, they go to this more advanced knowledge and more advanced courses and devices.
Yeah, exactly. So this this provides them with everything that they need to know to get familiar with the tools and to have a basic amount of success. It's easy to recreate the results for this. There's a set of hands-on labs that they go through. They can go through the labs without the hardware. Of course, it's always more satisfying when you can see the results on actual hardware. But yeah, I'd say those are a really great place for people to start if they have like if they have like 3 days or 6 days to dedicate towards their learning. This will absolutely get them familiar with the tools.
Yeah. Cool. So if a lot of people get this board and they want to sort of get onto maybe a live course with you guys, when is the next live course you're doing?
So things are a little bit more complicated now that we have like COVID, but we actually used to run in-person live events. So all around the globe, we have Avnet offices, and so we made those available, basically, to be run out of those Avnet offices. So I don't know if we'll ever get back to doing those live
on
events.
Zoom, for example.
Well, I mean, all of our live events, you know, we usually broadcast those live events either through that Hackster.io community. So you can go to Hackster.io and look for events on there, or the Element 14 community. So like if you go to Element 14 and you keep an eye out for, you know, upcoming events on those platforms, those are usually where we do any of our live trainings that come out. And of course they get recorded as well. So that way folks can go back and watch them if they end up missing them.
Cool. That's good. I think you guys should be doing more live events, especially on the internet. I think it's easier for people to just join on a Zoom meeting than have to go to an actual live event. The most important thing is actually being able to ask questions, so that if somebody's stuck with development, that they can ask you guys, how do I sort of continue? How do I do this? How do I do that? You know.
Yeah.
So that could be very valuable.
So we do have on our Element 14 community site, we do have those support forums. So like we respond back to those forums. Any questions that are posted on those forums, we respond back to them like within 24 hours. So the turnaround time is pretty good. So if you go on here, there's that forum tab is the 4th tab over on that little tab bar. Right there, yeah, technical specification. Oh, sorry, a little bit further down there. Yep, right there. Yeah, so like my team, we all reply up to the support forum right here. So if you have anybody is asking a question, they can go here and they can ask your question, and we'll reply direct to them directly.
That's really good, Kevin. Thank you very much. We are coming to a close here. Our time is almost up. Okay. But it's been a really, really value-packed interview here. And I think we should definitely maybe talk more about this, depending on what people want to know more about. And I think this will help a lot of people to get started with your hardware.
Yeah, no, I'd be really interested to hear what your students have to say about that. And
definitely, I'll keep you.
If you have any feedback for us, please let us know. We're always looking to improve our content and help make things easier for people to get started.
Awesome. Thank you, Kevin.
Thank you, Martin. Have a good evening.
Have a good evening, you too. Bye-bye.
Thank you. Bye-bye.